So if you look at these vehicles and they go through the thermal profiles that they would normally have, they're going to degrade over time. They're going to have capacity loss. What we found was that actually preconditioning just the cabin for thermal comfort, for the personal comfort, actually reduced our capacity loss. So we regained 4% to 7% of our battery capacity over life by just conditioning the cabin, making the person comfortable, reducing the amount of time that those batteries spend at high temperature. So let's talk about the actual load and what we might want to do with these loads. So if you think about the energy required to pre-cool the cabin, we might run that system for the 20-minute period before we hop into the car. And we assumed a 1,500 watt load, hairdryer type thing like Jan was saying, on a 110 circuit. That might be what you have. It's about 500 watt hours. The trip energy, how much energy you're using when you're driving, if you say about 20-mile drive and 275 or 300 watt hours per mile is a typical number, we've got 5,500 watt hours. So about 10% of our energy that we consume for that vehicle might actually go to preconditioning the vehicle if we do this in a very intelligent way. If for some reason we don't predict when you're going to be out there, we might have to redo the preconditioning a couple times to make sure that it is in a comfortable state when you actually get to your car. So that's kind of the good side. But again, the preconditioning may give us an extra 5 to 10% improvement in our range performance of the vehicle. The other piece to keep in mind, and this is just a pictorial thing on the bottom, the different periods where we preconditioning and charging, and then put a typical grid load shape on top of that. The preconditioning piece is probably not something that we're flexible on because we want that to happen exactly when we get to the car. And so there's probably no flexibility. The charging piece, it's a couple hours of charging while the car's parked there for 8, 10 hours, whatever. We probably have some flexibility in that. And flexible load is a valuable resource to utilities. So if you think about these two pieces, the preconditioning is probably something that utilities will have to learn how to adapt to. Charging is probably something that we can work with as engineers. This is an example of what you can do with that charge shaping and that ability to move charge around. The two charts here, we looked at the components in the grid infrastructure. The distribution transformer at a residence is the last component really in the system that is closest to the load and is probably going to be most impacted by the rollout of plug-in vehicles. This example, these are two examples. One where we looked at the overlay of the load. The green is basically residential load profile of a collection of homes on a residential transformer. The red is a group of plug-in hybrid vehicles at those homes overlaid on top of that household load profile, tacked on top of it. And then the green and the black lines are the thermal profiles of the transformer. So you can model the thermal characteristics of the residential transformer based on the new loads that are occurring on that system. And the green is without the plug-in hybrids, the black is with the plug-in hybrids. The dotted line there is a threshold temperature that means accelerated degradation of the transformer over time. And so the two cases here, one is just letting things happen the way they are. The one on the right-hand side is where we could do smart charging, smart control of those loads based on the thermal conditions of the transformer. All we did was a very simple delay mechanism. Give them a 10-minute delay. Once the temperature of the transfer comes down, we continue the charging event. There's plenty of time in the evening to finish charging all of the vehicles that were on this grid. So even though there may be issues, there's lots of strategies to deal with those issues. The last two pieces I'll talk about is the value of connecting vehicles and renewables together. Again, thinking about this in a systems context, we need to figure out how to find and create value from these two things. DOE has two goals in their program. One is in their vehicle technologies program. One is find a way to reduce our petroleum consumption by 50%. Plug-in hybrids do a pretty good job of getting us pretty close to that in terms of reducing our petroleum consumption. But the longer term goal, 80% of our energy from non-carbon sources. That's a challenge. How do we figure out how to get the vehicle energy tied into non-carbon electrical resources or fuel sources? Biofuels, hydrogen, whatever they may be, we got to figure out how do we tie those two pieces together. And the last bullet I put on there is if we're doing charge management, we're able to move these loads around, or we're even doing vehicle to grid where we're feeding energy back. What kinds of values, how do we account for the greenhouse gas emissions if that had some influential impact of increasing the penetration or reducing the integration costs of renewable energy? The chart I show is the comparative CO2 emissions of the different vehicle resources technologies on different electrical resources. The last bar on the far right is the plug-in vehicles fueled with renewables from the recent EPRI report. So it's one step down in terms of finding a way to reduce our emissions there. How do we do this? What really has to happen is you need to find a way to tie together vehicles, energy storage technology, and the plug-in vehicles with the renewable resources that we have. The piece that's really challenging or missing today is that communications utility interface. How do we know what's going on with solar? How do we know what's going on with the wind? And where are the vehicles? You need to understand all of these pieces of information and tie them together. How timely this announcement from Toyota and Microsoft today. That communication, data flow, information management is really the key to this technology moving forward and creating value. So here's the example that Jan was talking about at NREL. We, with the major growth that's happened at the lab, we also are building an 1,800 spot parking structure. That parking structure will accommodate a large portion of our vehicles. From opening, we've made it that this parking structure has to be the most technology-intense parking structure to be ever built. It has a 1 megawatt solar array on top. It has advanced lighting that is area specific. It has traffic flow lights so that we only use the sections that actually need to be used at any one time. And we have the ability to integrate plug-in hybrid electric vehicles into this system with energy management technology. The two charts I have here, we did a very quick analysis using NREL employee commuter data. We know how far people drive, where they live, and so on. The two charts, the blue line is basically 20% of employees, and we selectively looked at driving profiles and tied them to the technology options available. Showing up on campus and immediately charging their vehicles. And that's a 700 kilowatt load. Well, the transformer for this building and for these vehicles is only a 500 kilowatt transformer. So we have to be creative. The green line is basically taking those vehicles and creating a staggered charging strategy between all those vehicles. We know the employees are going to be there. So let's take advantage of the fact that we know that and manage the charging so that we still get everybody's cars charged. We minimize the infrastructure costs. And if you look at it, it looks just like the solar array load. So now those vehicles you could, in theory, tie into your solar generation on campus. And the chart on the right is basically how long individual vehicles had to wait to do charging. So most of the vehicles, 60 of the 240 in this case, I think it was, charged instantly, immediately. And some of those vehicles had to wait up to 1 to 3 hours, but they still all got charged. The curve the green curve going to 0 shows that all vehicles were charged by 4 p.m. So I think we did a pretty good job of matching things together there. I'll wrap up with just a couple slides here. Integrating systems is the theme that really needs to go forward to create value. You need to find a way over this transition from going from our current power situation, grid system with a few green vehicles out there, to a system where we've got a lot of renewables on board the system with new vehicles and charging infrastructure, both at our businesses, workplaces, and homes. And then the last step in here, tying that all together with communications infrastructure, being able to communicate what's going on so that people feel like they're getting value from the system as a whole. So the last piece, one thing that I talk to utilities about a lot when they talk about plug-in vehicles, they get kind of scared. They wonder, well, what's this going to be? And is there an uncertainty of it? How's it going to influence our infrastructure? The biggest piece, get the vehicles connected and let them be a flexible load. Find a way to create a system that people are comfortable that the car will be charged, but it's a flexible system. So it's great that there's this coincident timing with smart grid technology, renewable technology, and the PEVs coming out at the same time, because I think it's an opportunity to really tie all the systems together. Jan talked about diversity factors. Travel diversity is a really important factor in accommodating a lot of these loads. Not everyone shows up at home at 4 o'clock and charges their vehicle. Those transformer load characteristics I showed, they didn't look like a big step curve. They're a bell curve because people show up at different times and we plug in our vehicles at different times. There's a lot of opportunity for being flexible in the load delivery time frames. The PEVs are really a new interface point. We're talking about utilities, buildings, customers, everybody kind of connecting pieces together, and it's a point of interface, it's a point of creating data, it's a point of handing off data and being able to do something about that information. And the last piece there is on the preconditioning. There's obviously value in comfort for the consumer. There's value for making the batteries comfortable, and again, it's about value creation. So I'm going to leave it at that, and we'll see what kind of questions come up. Thank you.